I'm going to sit down, I think. It's been standing all morning on the stand, G64, I think it is, just over there. So my name is Stephen Crozier. I'm CEO of RheEnergise, and we're developing a long-duration energy storage technology that we call high-density hydro. We have offices in London and a subsidiary in Montreal in Canada, which is the heart of the hydropower industry. I've got to make sure I get the right clicker. So here we are. So we all know that the world is seeing damaging effects of climate change. And we also know that there is a solution in the form of renewable energy, but that presents a new problem, that of intermittency. The need, commentators from around the world, I'm going to stand up because I feel slightly uncomfortable sitting down. So commentators from all across the world have recognized the need for long duration energy storage. The long duration energy storage talk about a $4 trillion market, 8,000 gigawatts by 2040, which is just 17 years. So the question is, how many markets are predicted to grow tenfold in 7 years and maybe 40-fold in 17 years? And also the predicted opportunity for 540 billion of annual savings to consumers by the deployment of long duration energy storage. So in order for the energy transition to succeed, we need an absolutely massive amount of energy storage. So the problem is really about scalability, finding solutions that can scale fast enough and at the speed that the energy crisis demands, the climate crisis demand. So what is high-density hydro? So it's very like traditional pumped hydro. Traditional pumped hydro is where you have a reservoir at the top of a mountain behind a dam and a reservoir at the bottom. And when energy is abundant, water is pumped up, and when energy is scarce, it's released and electricity regenerated through a turbine. So what high-density hydro does is very much the same thing, but rather than using water, we've introduced a fluid 2.5 times the density of water. So the introduction of that fluid in a closed loop system, what that does, it means that we can reduce the vertical elevation by up to 60%, and that gives us several orders of magnitudes more siting opportunities. Or alternative, we can reduce the footprint of a project, again, by up to 60%, and this means projects are faster to consent, faster to build, and lower cost. So when we think of traditional pumped hydro projects, we think of massive projects in mountainous areas, 10 years or so to consent, 7 years to construct, large amounts of water abstraction, lack of sites, long distances from generation and demand. It's a very good solution. It's a very low-cost solution, but it's not scalable fast enough to meet the demands of the climate crisis. So RheEnergise's high-density hydro is different. We can install projects on small hills rather than mountains. And these are some examples of what... it's not clicking forward. This is an example of what a project site might look like rather than mountains in protected areas. So long-duration energy storage, it's a solution for all sorts of locations across the world. It can be connected, co-located with wind and solar farms. It can be used for optimizing transmission and distribution grid investment. It can balance base loads. It can be installed on energy islands or real island grids, or supporting industries across the world. So, as the percentage of renewable energy generation increases on a grid, what project developers find is that the value of their energy that they're exporting to the grid declines over time. As there are more and more projects, the value of that energy declines. And this has been seen on many grids across the world. And therefore, the developers' revenues fall from a project that they've installed. We also see this on the UK grid, whereby we can regularly see the impacts of solar and wind on the UK grid, dramatically reducing wholesale energy prices. So this is great for the consumer, but it's not so good for the developers. If they can't capture good energy prices, then they won't install future projects and we won't achieve the decarbonisation that is needed. This is another graph which dramatically illustrates the problem that they have in Chile, where last year they had 1,600 hours of zero price electricity. So as your consumer, that would be really good, but from a developer perspective, they are really desperate for a solution for energy storage so that they can dispatch the energy generated during the day at much higher values, either in the evening peak, overnight, or during the morning. So what's happening in Chile is just a little bit in advance is what's going to happen in other countries. We're beginning to see it in Spain. It's not far off in the UK. The UK is somewhat different because we are more heavily reliant on wind. But it doesn't matter what the form of renewable energy generation is. There's intermittency in it, and you need to be able to store that energy. So often we get asked about how we compare to lithium-ion batteries, and lithium-ion batteries are a great solution for short duration. But what you find with lithium-ion batteries, as you increase the duration, that the projects get progressively more and more expensive. So if you're looking to store 1, 2, 3 hours of storage, then lithium-ion batteries are a great solution for that. If you're looking for longer duration storage to match the daily cycles of wind, or the daily cycles of solar, or the twice weekly cycles of wind, you need much longer energy storage. So high-density hydro, RheEnergise's solution, we fit into what we call the medium duration market. So short duration probably will be dominated by lithium-ion batteries and some other solutions coming through. Interseasonal storage will probably ultimately become green hydrogen. But the heavy lifting on the grid needs to be done by a low-cost solution that's going to shift the daily cycle of solar or the twice-weekly cycle of wind. And that's where we come in. And so we believe that the 4 to 16 hours of duration will probably shift around 70% of the energy volumes needed per annum in somewhere like the UK, Spain, any other market. This is a piece of work by a consultancy firm, Jacobs. So what they've done is developed a methodology called the unit cost of firm generation. And what they looked at, so this methodology is very similar to levelized cost of storage, but rather than using a fixed energy price, they did an analysis with a variable energy price from renewables on the UK grid. And what they found is that lithium-ion battery is a great solution for up to about 3 hours, and then other forms of energy storage to create firm baseload became increasingly more attractive. And if you could do pumped hydro, it was consistently and by a large margin the lowest cost form of energy storage, or the lowest cost way of creating firm supply from a renewable powered grid. And then at something like 12 hours of storage, the cost gap between traditional pumped hydro and lithium-ion batteries is in the order of £200 per megawatt hour. And this is wholesale. So retail prices are probably something like 2.5 times that. And so if you want consumers to be happy and industry to be happy, you need low-cost generation solutions, which we already have, but you need low-cost storage solutions to day in, day out, shift energy consistently, reliably. And then where does RheEnergise sit on this? So our own projections, looking at our capital cost, operational costs of projects, suggest that we closely match the performance of traditional pumped hydro in terms of levelized cost of storage, or in this case, unit cost of firm generation. So one of the questions we're regularly asked is, how many sites? What are the opportunities for this? And so every country we've looked at across the world, we find an abundance of sites. So the scale on the bottom left is every country in the world. So I can't remember which country has 181,000 sites. But across Europe, we find that most countries are, 5 to 20,000 sites. Turkey is the largest in Europe with about 20,000, France 12 or thereabouts, Spain somewhere similar. Spain 13,500. So the UK, we predict there are 6,500 sites roughly. And to put that into some sort of context about how many sites do you need to develop, so we think something like 300 to 350 high-density hydro projects provide around 10 gigawatts of storage, and this is around 25% of the predicted energy storage needs, according to the consultancy Aurora. So with a relatively small number of projects, and again, to put that in context, how am I doing for time? To put that in context, we have 2,000 operational wind farms, so building 350 odd projects to achieve a significant difference in the energy storage needs in the UK is impressive. Going to go very quickly. So our test site, so we have government funding, £8.25 million of government funding to do a significant amount of R&D, and then on this site at the top, build a 500 kilowatt, 1 megawatt hour project. That should be operational spring next year. And then we've done a lot of testing at our facility or near our facility in Montreal, Canada. So this is where we do our outdoor testing in Montreal. This is some of our laboratory, some of our other team. So we do mechanical electrical engineering in Canada, formulation chemistry with the University of Greenwich, operation commercial functions out of Europe. This is some of our team, 4 entrepreneurs, 4 doctors, 2 MBAs, 2 chartered accountants. We have a very good, impressive team growing all the time. I've probably got to skip over this if I've got to get questions. So last slide, we're currently fundraising. We're doing a Series A, 6 to 10 million pounds we're seeking, which is really to accelerate the growth of our business, to get to market faster, quicker, and happy to have a conversation with anyone who's interested in investment. Welcome any question.
What are some of the siting concerns, and what's the land print required for the system?
So siting requirements. So the scale of projects we're looking at doing is 10 to 100 megawatts of power, and 4 to 16 hours of storage is our sweet spot in terms of a project. So the footprint is quite variable. So a small project, we will probably be something like a hectare of land, top and bottom. Big projects, significantly bigger than that. In terms, one thing to recognise with hydropower and high-density hydro is when you double the vertical elevation, you halve the physical size of a project. So the envelope we look at in terms of vertical elevation is 75 to 300 metres. So a project at 300 metres is 1/4 of the size of a project at 75 metres. So the reason why we cut off at 75 metres, it's not really a technical barrier. It's all to do with the footprint. It just gets larger and larger. And the economic case starts to break down because we're not using water, we're using a high density fluid, and there's a sample on the stand. Because we have to procure that fluid, that the economics starts to break down at very low elevations. The projects just get much bigger.
Quick one, obvious question, but what's the carbon footprint of the fluid?
What's the carbon footprint of
the fluid?
Of the fluid. So it depends how we get it. So we also have a second grant-funded project to look at using waste material from other industries. So that's a £1.5 million project. We're working with the Camden School of Mines and the University of Greenwich and looking for waste streams from other industries. So the additional carbon footprint of that would be very small. So there is some, but if we're using...
As a percentage of the whole cost? Because everything else is about the same as water, isn't it?
Yeah, I don't have that number in my head, but we did do a piece of work with an economist at the University of Brighton a year and a half ago now, and he looked at it comparative to solar plus batteries, solar plus traditional pumped hydro, solar plus us as a sort of and we came out looking very good, but I don't have the exact numbers in my head to be able to give you anything with confidence.
I have time for one more quick question. Any more questions? No?
I'll answer a question we're always asked. Is the fluid environmentally benign? Or what the fluid is. So the fluid is a suspended solid in water. So it's a fine milled mineral suspended in water, which is where our IP is, how you suspend that. So have a high density but low viscosity. And then We've had our fluid independently tested by 2 UK laboratories as environmentally benign, so it's also non-corrosive, non-reactive, etc. And that has been accepted in the planning permission we've been granted down at our test site in Devon, those certificates.
I think you can maybe take that offline. Thank you very much, Stephen.
Thank you, everyone.